In lab, you guys were looking at pressure and how pressure varied with depth. But before we get into that, I made a claim at the beginning of the lab that the pressure in a fluid at any given height is constant. That means if I look at this height, that was supposed to be a level straight line, that the pressure here, 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 they're all the same. Okay? And if you think about that, let's say that the pressure over here was actually greater than the pressure here. Well, that would cause a net flow in water, right? Because if the pressure is greater on one side, that's going to push, and this thing's going to start moving that way. And then we would get this flow of water. But we don't get a flow of water in the glass. It's constantly, it's static, it's at rest, so it's a constant pressure. However, we did notice if we forced the tube further and further and further down into this water, that the pressure increased and went higher and higher and higher and higher. So we got to think about why that happened. Okay? So let's take a look at what we actually did. We took a graduated cylinder, kind of a big one, 1 liter graduated cylinder, and we filled it mostly up with water. So we had a level of water in here about here. And then we took a second tube, connected it to a pressure sensor, and we forced it down into this tube. And we went 5 centimeters, 5 centimeters, 5 centimeters, getting deeper and deeper and deeper and deeper. Now hopefully you guys noticed, as you forced this tube down, the water level actually stayed right here inside this tube. It was always at the same level as the water around it. And that's sort of an interesting thing, okay? Because this tube is actually full of air, and when you start pushing it in there, there's water actually pushing up into this tube. These little particles of water come in here. They're pushing the air up, which is causing that increase in pressure that we measured. Okay? But that's an interesting thing, because really that means this column of water, it's in a gravitational field, it should fall out. Okay? Gravity is pulling down on it, and in fact we can figure out the amount of gravity pulling down on it. We call that weight, right? And we know from physics 1, weight is equal to mass times the acceleration due to gravity. I don't know the mass of that section of water or that fluid, whatever it is, but there's an easy way to get mass, right? If I know the height, the height of this thing, which is from here to here, that's the height of my column of water, then I can figure out its weight, because the area of the tube is A, and the height is h, which tells me the volume of the tube is A times h. And since it's a fluid, water, I know its density. And remember, density, rho, is equal to mass over volume, which means if I multiply both sides of this equation by v, volume times density gets me mass. And I can substitute that into this equation, and I can substitute this into this equation, which means really the weight of that column of water is equal to its volume, or the area of the tube, times its height, times its density, times the acceleration due to gravity. Okay, that's the weight of that water. And since it's at rest, it's in equilibrium, that means the force pushing up on it and the force pulling down on it have to be constant. Well, what is exerting this force up? Well, it has to be, there's only one other thing there. It has to be the fluid pressure of the water around it. So if we know what the weight of this column of water is, we also know how much force is pushing up on the bottom of this open tube, okay? Which means this is equal to the force from this fluid. But that only makes sense if we know how much area it's acting over, and so we're going to do this in terms of pressure. So the force is acting over an area of the tube, which means if I divided this side by A, I have to divide this side by A. So force over area, which is equal to pressure, that's a capital P, is equal to rho, the density of the fluid, times g, the acceleration due to gravity, times h, the height of the column, and the a's cancel. Now this right here, pressure equals rho gh, is actually an incredibly simplistic and powerful tool. It's interesting that the pressure of this column of water does not depend on the overall area of the tube. It only depends on the density of the fluid, depends on the acceleration due to gravity, and it depends on the height of the column. Okay, and what's interesting about that is if you think about a really large lake, like one that's really long but kind of shallow, and so we have a dam over here on one side. This is my dam. Okay. how much pressure is at the bottom of that dam? Does it matter that this lake is really, 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 really long? No, it doesn't. It matters how deep the water is. Okay? If the lake is deep, then there's a lot of pressure at the bottom. If the lake is not very deep, there's not so much pressure at the bottom. So, you know, this lake that's really long but kind of shallow doesn't have that much pressure. But if I had a different lake that was short but really, really deep, okay, then it's going to have more pressure because it's deeper. That water has a greater height. So the pressure from a fluid is rho, its density, times g times height. Now, last thing I asked you guys to do in lab was compare this to what you did with your results. Now, when you actually measured the pressure in there, you got a line, y equals mx plus b, and you had values for all of these. Y was pressure, m is slope. I'm not going to use, well, all right, yeah. I'll use m for slope. X was height, h. And then we had this mysterious plus b. What is that? Why wasn't it 0, right? Because before we even put this thing into the water, we had pressure. Well, that pressure arises because we have an atmosphere. Okay, and an atmosphere of pressure is the pressure from the air around us, right? It's a fluid. Air's a fluid. It's exerting a pressure. One atmosphere is right around 101 kilopascals. Now you'll notice you probably measured something below 101. It was probably closer to 93, 94. Well, this is at sea level, right? We're not at sea level. We're a couple thousand feet above sea level. So just like the fluid pressure in water changes with depth, the fluid pressure in air changes with depth. So we're higher up in our column. There's less air above us. There's less atmospheric pressure. Now, this leads to a thing that we call gauge versus atmospheric pressure. If you think about a tire, okay, we put air in our tires, but there's already air in it, right? There's a pressure on the outside of this tire from the atmosphere, but it doesn't collapse and just crush in on itself. Even if it's a flat tire, really, if there's no weight on it, then it still stays in the shape of a tire. That's because there's still atmospheric pressure acting out on it too. So when we say we put 30 psi, or about 230 kilopascals, into a tire, what we mean is we put 230 more. Okay, so the pressure in here is 230 kPa higher than the pressure out here. So the pressure out here is not 0, but we're measuring relative to that, and that's what we call gauge pressure. Okay, gauge pressure is pressure above atmospheric pressure. Above atmosphere. Now, if we want the total pressure, which is how much pressure is actually acting, including that, then total pressure is atmospheric pressure plus gauge pressure. And depends on the problem. Sometimes all we care about is gauge pressure. A lot of times all we care about is gauge pressure because atmospheric pressure acts on everything, and for most applications it's the depth change is not enough for an appreciable difference. Now, that's the plus B. It's that constant, that atmospheric pressure that's there. So we actually were measuring total pressure. If we'd have said 0 is air pressure, then we'd have been measuring gauge pressure. But you'll notice this equation, MH, does not measure what we saw, where we saw the pressure was equal to rho GH. Well, that's because the slope of your line is actually rho G. So if you take your slope, whatever it was, and you divide it by G. Now you've got to be very, very careful here. Make sure all your units are matching. What you should come up with is the density of water, because that's the fluid you were in. Now when I say you got to be careful with your units, let's see, I believe that you had units on your slope. If you were measuring the pressure in kilopascals and you were measuring the height in centimeters, then this is your unit, which is a really weird unit. And there's a lot of things that are going on in there. Remember, a Pascal is a Newton per square meter. So if I had kilopascals, what I really have is this is 1,000 newtons per meter squared per centimeter, but I don't want centimeters because I have meters up here now, which means I'm going to use 0.01, right? 0.01 centimeters is 1 meter. Well, now I've got to change some math and do some stuff, right? So I divide 1,000 by 0.01 and I get 1,000 with 2 more decimal places. So now I have 100,000 newtons, and this meter squared divided by a meter is a meter cubed. All right, keep going. So 1 kPa per centimeter is where we started. Now we're at 100,000 newtons per cubic meter. But a newton is not a base unit, and Newton is a derived unit. So remember, 1 Newton is a kilogram meter per second squared. All right, so now I can replace this with that. So this is 100,000 kilogram meters per second squared per meter cubed. All right, well, this meter cancels one of these, so we're left with a square. So I have 100,000 kilograms per meter squared second squared. Now, I said that you're going to divide this by g. Okay, so later you're going to notice if you divide this by g, you'll get the density of water. So if I just multiply times 1 over 9.8 divide by g, right, multiplied by the reciprocal, which is seconds squared per meter, you'll notice my seconds squared cancels my seconds squared, and this meter times that meter is going to leave me with meters cubed, which is going to leave me with kilogram meters cubed, which is a density. So it is a long derivation for that, but if you divide your slope by g and make sure all your units match, you should come up with something close to the density of water.